Mathematical modeling for height calculation. Welcome, everyone. Today, we are going to explore a very practical application of trigonometry, mathematical modeling for height calculation. Now, think about the world around you. If you wanted to find out exactly how tall a local monument, a massive mobile tower, or a skyscraper is, you'd quickly realize that you can't simply climb to the top with a measuring tape. In real-world scenarios, it is often physically impossible or just highly impractical to measure the height of such tall objects directly. So, how do we solve a problem that seems impossible to measure? We use a technique called mathematical modeling. Instead of dealing with the complex physical structure of a tower, we simplify the situation. We represent the physical scene as a geometric figure, specifically a right-angled triangle. By doing this, we can use our knowledge of trigonometric ratios to calculate the unknown height with great precision. Over the next few slides, I will show you exactly how to set up this model and solve these problems step by step. The core concept. When you're standing there looking up at the top of a tall object, like a tower, your line of sight doesn't actually start from the ground at your feet, it starts from your eyes. This is a crucial detail. Because your eyes are positioned some distance above the ground, the triangle we are about to build doesn't cover the entire height of the object. It only covers the part from your eye level upwards. Therefore, to find the actual, total height of the object, we must remember to account for the height of the observer as well. So, if we want to determine the height of an object, let's call it CD. Without actually climbing it, we need three specific pieces of information. First, we need the distance from the observer to the foot of the object. This is the horizontal distance on the ground between you and the base of the tower, which we can label as distance, DE. Second, we need the angle of elevation. This is the angle formed between your horizontal line of sight, the straight line looking out from your eyes, and your line of sight looking up toward the top of the object. We can represent this angle as angle BAC. And finally, we need the height of the observer. This is the vertical distance from the ground up to your eye level, which we will denote as height, AE. Now that we understand that we use mathematical modeling to turn real-world objects into triangles, let's look at the core concept that often trips students up. Keep these three components in mind, because in the next slide, I will show you exactly how we use them to step-by-step construct our mathematical model. Step-by-step modeling process. First, step 1, establish the observer's position. Before we look at the tower, we must identify the height of the person standing there. We'll denote the observer's height as a E. Think of this as a constant vertical line representing the distance from the ground up to the observer's eye. Next, step 2, create a horizontal reference line. To make our calculations easier, we need a flat baseline. Imagine drawing a horizontal line starting from the observer's eye, which we've labeled point E, and extending it until it meets the object at point B now, because the observer is standing vertically. This line, EB, is parallel to the ground. Line D, this is a crucial point. It means the length of our line EB is exactly the same as the distance from the observer's feet to the base of the object, which is ED. Finally, step 3, form the right-angled triangle. This is the most important part of the model. We are only interested in the part of the object that is above the observer's eye level. The section from point B up to the top, point C, creates a right-angled triangle, delta EBC in this triangle. The side BC represents the opposite side, which is the partial height we need to find. The side EB is our adjacent side, representing the horizontal distance. And the angle CEB, is our angle of elevation. Now that we understand the core concept, specifically that we cannot ignore the observer's eye level, let's walk through the actual modeling process step by step. This is where we translate a real-world scene into a mathematical diagram. Once we have this triangle constructed, we'll be ready to move on to the next slide, where we'll use trigonometry to actually calculate that partial height. Step-by-step modeling process continued. Step 4 is where we calculate the partial height. Remember, we aren't looking for the full height of the tower yet, just the portion that sits above your eye level, which we labeled as BC. To find this, we use the tangent ratio. Since we know the angle of elevation and the horizontal distance, we can set up our equation as tangent of the angle of elevation equals the opposite side divided by the adjacent side, which in our specific model is BC divided by EB. Once you have solved that equation for BC, we move to the final, crucial step. Step 5, determining the total height. It is very important not to stop at the value of BC. As we discussed in the earlier slides, the observer's eyes are not on the ground, they are at a certain height above it. Therefore, the total height of the object, which we call CD, is the sum of the partial height we just calculated, BC, and the distance from the base of the object to the eye level, which is BD. Now, if you look back at our model, you'll see that the segment BD is exactly the same as the observer's height, I. So, to make things simple, our final formula for the total height is CD equals CB plus I. Once we apply the numbers in our upcoming example, you'll see exactly how this works in practice. Now that we have successfully modeled our scenario and identified our right-angled triangle in the previous step, let's move on to the actual calculation. Real-world example. Imagine this scenario. A student, who is 1.5 meters tall, is standing 20 meters away from the base of a minar. As the student looks up toward the top of the minar, the angle of elevation from their eye level is 30 degrees. Our goal here is to determine the total height of the minar. To solve this, we'll follow the step-by-step method we just discussed. The first thing we need to do is identify our given values from the problem. First, we note the height of the observer, which we labeled as a E, is 1.5 meters. Second, we identify the horizontal distance from the student to the foot of the minar, which is ED, as 20 meters. And finally, we have our angle of elevation, theta, which is 30 degrees. Now that we understand the theory and the modeling process, let's put everything we've learned into practice with a real-world example. Keep these values in mind, because in the next slide, we are going to use them to set up our right-angled triangle and calculate the height. Real-world example continued. First, let's set up our triangle. Remember, as we discussed in our modeling process, we aren't looking at the whole minar yet. We are focusing on the part that sits above the student's eye level. So, let's let the height of the minar from the eye level up to the top be represented by BC. For our horizontal distance, the distance from the student to the minar, which we called ED, is the same as the distance from the eye level to the tower, which is EB. So EB equals ID, which is 20 meters. Next, we apply our trigonometric ratio. Since we are dealing with the side opposite to our angle and the side adjacent to it, we will use the tangent ratio in triangle EBC. We write this as tangent of 30 degrees equals BC divided by EB. Now, substituting our known value, we get 1 over the square root of 3 equals BC divided by 20. To isolate BC, we multiply both sides by 20, which gives us BC equals 20 divided by the square root of 3 meters. Finally, to make this number useful, we need to rationalize and calculate the decimal value. If we take the square root of 3 to be approximately 1.732, then 20 divided by 1.732 gives us a partial height of approximately 11.55 meters. Now that we have identified our known values from the previous slide, the student's height, the distance from the minar, and our angle of elevation, let's move into the actual calculation. Keep this number in mind, because in the next slide, we have one very important final step to find the total height of the minar. Real-world example continued. Now that we have successfully calculated the partial height of the minar above the student's eye level, we are on the very last step of our calculation. Remember, as we discussed in our modeling process earlier, the value we just found, BC, only represents the height from the eye level upwards. To find the actual, total height of the minar, which we call CD, we must add the height of the observer back into our result. So, the formula for the total height CD is equal to BC plus I. Plugging in our specific values from this problem, we take our calculated partial height of 11.55 meters and add the student's height of 1.5 meters. When we perform this addition, we get a final result of 13.05 meters. Therefore, our final answer is that the total height of the minar is approximately 13.05 meters. In the next slide, we will wrap up this lesson by reviewing the key takeaways and looking at some common pitfalls to avoid in future problems. Key takeaways. First, let's revisit the idea of modeling. Remember, when we face real-world height problems, like measuring a skyscraper or a tower, we don't actually climb them. Instead, we solve these problems by converting the physical scene into a geometric model, specifically a right-angled triangle. This simplification is what allows us to use trigonometry effectively. Next, I want to emphasize what I call the eye-level factor. This is a crucial detail. When you are calculating the angle of elevation, always remember that this angle starts from the observer's eye level, not from the ground. If you forget this, your entire calculation will be off. Now let's look at the master formula we've developed through our steps. To find the total height, you take the horizontal distance, multiply it by the tangent of the angle of theta, and then, most importantly, add the observer's height. So the formula is total height equals the quantity, distance times tangent of theta plus the observer's height. Finally, keep this principle of geometric equality in mind. In our models, the horizontal distance from the observer's feet to the base of the object is exactly equal to the length of the horizontal line we draw from the eye to the object. This equality is what allows us to use that distance as our adjacent side in our tangent ratio. All right, class, as we wrap up this lesson, let's take a moment to review the key takeaways from today's session to ensure you have a solid grasp of the concept. Keep these points in mind as we move into our next topic, where we will look at some common pitfalls and mistakes to avoid during your exams. Common mistakes to avoid. Now, before we wrap up today's lesson, I want to touch upon some common pitfalls. Even if you understand the concept of mathematical modeling, it is very easy to make small errors that lead to incorrect answers. First, the most frequent mistake I see is ignoring the observer's height. When you perform your calculations, you are often finding the length of side BC, which is just the part of the object that sits above your eye level. If you stop there and forget to add the observer's height, which we call the E, your final answer will be incomplete. Remember, your calculation gives you the partial height. You must add that initial vertical distance from the ground to the eye to find the true, total height of the object. Second, be very careful with your ratio selection. I have seen many students mistakenly use sine or cosine. Remember, in our modeling process, we are usually dealing with the relationship between the opposite side, which is the partial height, and the adjacent side, which is the horizontal distance. Because of this, tangent or its reciprocal, cotangent, are almost always your best tools. Only switch to sine or cosine if the problem specifically provides or asks for the length of the hypotenuse, which is the actual line of sight. Finally, watch out for misplacing the angle. The angle of elevation is not located at the base of the tower or the minar. It is specifically the angle formed at the observer's eye level. When you are sketching your diagram, ensure that your angle is placed at point E, where the horizontal line of sight meets the line of sight to the top. Keep these 3 points in mind, and you will avoid the most common traps in trigonometry.